So now that we've completed the foldable on identifying linear functions by looking at the table, equation, and graph, I would just want to do some additional examples. And also want to start with first writing the definition of a linear function. So, a linear function. All right, so a linear function has two parts to it because first of all, it has to be a function. So this is a set where all x's are different, because that's what it means to be a function. So it has to be a set where all x's are different and make a line on the graph. So what we, sorry about that. So what we looked at on the foldable is if we have a graph, it's easy to see that a linear function is a linear function because on a graph we would have a straight line. So what we looked at on our foldable, which I'm going to put right here for a second, was how to identify with a table. And if you can think to yourself, hopefully you remember, that a table will have a common difference between the x's and the y's. And then looking with an equation, instead of making a list of what a linear equation will look like, we have a list of all the things that a linear equation will not have in it. So what I want to do is write on our notebook paper the types of things that would look like a linear equation. So some examples of linear functions would be looking at the equation. So here are equation examples. Let's say that we had y equals 12x plus 7. That would make a linear equation. 3y minus 2x equals 10. That would be a linear equation. Y equals 19 would be a linear equation. X equals 4y plus 8. That one is a linear equation, so I actually should say linear just to reiterate that these are all examples of linear functions looking at the equations. All right, so just to run through a few more examples. So I'm going to slide this up a little bit. So example, number 1 is, let's say that we had y equals 9 over x. So if you look back at your foldable, the foldable showed us the things that could not happen. So if we look at this, if we have the equation 9 over x, that looks similar to this. This is one of the items that will not be in a linear function. So this one is not linear. Now, it can still be a function, it's just not a linear function. All right, another example. Let's say that we had 3x minus 7y equals 21. Well, there aren't any exponents. The x and y are not multiplied together. There's not square roots. We have an x and a y in the equation, and it's not in a fraction form, so this one is linear, and it fits some of the examples that we had up here. All right, try another one. Let's say for example 3, how about y squared equals x minus 1? Well, if we start through the things that we can't have, I see an exponent, which is the first thing on our list of what not to have in a linear function. So I already know this is not linear. Now again, it could be a function, but it's not a linear function. All right, let's do one more of those. So example 4, what if we had x equals 7? All right, so again, if we look at what we are not going to have in a linear function, we don't have any exponents, x and y are not multiplied together, we don't have any square roots, but here's a problem. There's only an x in the equation. So there is no y, so this is not linear. Now, I mentioned when we were doing the foldable, this is a line, but it's not a linear function because it's a vertical line. And vertical lines don't pass the vertical line test. All right, let's try some examples of, move that up a little bit. Let's do some examples using the ordered pairs, or the t-tables, if you want to call them that. So just for space reasons, I'm going to set mine up going across horizontally, yikes, instead of going up and down. Okay, so let's just say -1, 17 is a point, 2, 13 is a point, 5, 9 is a point, and let's say 8, 5 is a point. And I'm just making these up. So, all right. What happens when we have a table of values is we want to check what's happening from one point to the next. So from this x to this, so from -1 to 2, that's an increase of 3. From 2 to 5 is an increase of 3. And from 5 to 8 is an increase of 3. So far that looks good. All right, let's check what's happening between the y values. From 17 to 13, that's subtracting 4. 13 to 9 is subtracting 4. And 9 to 5 is subtracting 4. So we have a common difference among the x's and the y's. That means this is linear. All right. Let's do, here's another one, example 6. So again, I'm going to set it up this way, going horizontal. Ooh, I didn't leave enough space, I don't think, in between that one and the last one. All right, let's say 7, 12 is a point, and 5, 9 could be a point, 3, 7, and let's say 1, 4. So we'll just pretend I didn't draw that quite so long. All right, so again, what we want to do is check to see what's happening in between the x values and the y values. All right, so right here, we're subtracting 2, right there, subtracting 2, right there, subtracting 2. So that looks okay. All right, looking at the y's, this looks like we're subtracting 3. That looks like we're subtracting 2. That looks like we're subtracting 3. So we have a consistent change on the x, but we don't have a common difference along the y's. So this is not linear. Now, we know that it is a function. All the x's are different. The problem is that even though all of the x's are different, there's not a consistent change in between the x's and the y's. All right, let's do one more of those, and then I'm going to say that you know what's going on. All right, so again, I'm going to go horizontal instead of vertical here. So how about 12, 0 is a point? Whoops. 13, 5 is a point. 14, 10, whoops, is a point. And then 16, 20 is a point. So let's go through and check out the differences between the x's and the y's. So from there to there, we add 1. From there to there, we add 1. From there to there, we add 2. So that doesn't look good so far, but let's see what happens among the y values. So from here to here, we add 5. From here to here, we add 5. From here to here, we're adding 10. So I kind of look and I notice, well, I went up 1 and added 5. I went up 1, I added 5. Here, we went up 2 and added 10, which is the same thing as going up 1 and then up 5 and then up another 1 and up another 5. So this, if you want to think of it, it kind of reduces. 10 divided by 2 would be 5. So this one is, in fact, linear. So even though the pattern wasn't consistent up here, it still actually is the same thing. It's almost like if you guys ever go up or down the stairs, sometimes you might take 2 steps at a time. So you're going up 2 steps in 1 foot length, whatever you want to call it, which obviously I'm not very good at because of my height, but you're able to walk up 2 steps at a time. You're not going any further than I am if I walk up at 1 step at a time. So that's kind of another way to think of it. All right, I don't think we need to go over any examples of graphing because, again, if it makes a straight line on a graph, it's a linear function. So at this point, you're done with your video and you can start on your assignment.